Hello, chemistry explorers. Did you hear about the aromatic compound that joined the band? Yeah, it formed a diazonium bond. It's a group that really knows how to rock and roll in synthesis. Today, we are diving into diazonium sols, those fascinating aromatic compounds with the functional group N2 positive X negative. Imagine this as a nitrogen duo, two nitrogen atoms with a positive charge paired with a negative counter ion like chloride or bromide. These salts typically come from primary aromatic amines, which are like the trusted starting players in this chemical concert. Now, how do we get these diazonium salts? Through a process called diazotization, where primary aryl amines are treated with nitrous acid, HNO2, at chilly temperatures, specifically between 273 to 278 Kelvin or just above freezing. Think of it as a chemical winter recipe that works best when it's cold. But wait, nitrous acid isn't just handed to us, we make it right there in the reaction mixture. By mixing sodium nitrite, which is NaNO2, with dilute hydrochloric acid or HCl, the reaction goes like this. Sodium nitrite plus hydrochloric acid gives us the magical nitrous acid HNO2 plus sodium chloride, which is ordinary table salt, nothing fancy. Once this nitrous acid is formed in the solution, it reacts with aniline, which is a primary aromatic amine, specifically C6H5NH2, to deliver benzene diazonium chloride. The equation sounds like this. Benzene amine plus nitrous acid plus hydrochloric acid yields benzene diazonium chloride plus 2 water molecules. So, aromatic amines get converted into these versatile diazonium salts under cold, acidic conditions. Picture the reaction scheme in your mind: aniline reacting with freshly formed nitrous acid in an acidic bath, producing benzene diazonium chloride, with the nitrogen replacing the amino group and ready to participate in further exciting chemistry. This reaction is fundamental because diazonium salts act like highly reactive intermediates, opening doors to synthesizing a wide variety of aromatic compounds. It's a bit like setting the stage for a series of clever transformations in the lab. Welcome back, curious chemists. I have a question. Why don't diazonium salts crash the party by themselves? Because they're a bit too unstable. Yes, aromatic diazonium salts are thermally unstable youngsters. They prefer to hang out only at low temperatures because heat makes them fall apart, literally. But here's the cool part: even though they're unstable, they are extremely useful and react instantly with suitable partners in different reactions when kept cool. The diazonium group, which is this nitrogen pair with a positive charge, acts like a perfect leaving group. It's the chemistry equivalent of a passerby who just wants to leave the party gracefully, making room for new guests. This leaving group property helps in nucleophilic substitution reactions, kind of like swapping a friend in and out of a fun game. Now, why does this swap happen so smoothly? Because when the diazonium group leaves, it escapes as nitrogen gas, N2, which is incredibly stable and just floats away. This expulsion of nitrogen gas makes the reaction practically irreversible, pushing the reaction forward like a fast-moving train. Imagine the simplified equation: aromatic diazonium salt decomposes to an aryl compound, ARX, plus nitrogen gas bubbling out. What's more, these salts are like VIP passes that let chemists introduce various substituents onto the aromatic ring under controlled conditions. It's a tried-and-true method to customize aromatic compounds for dyes, pharmaceuticals, and more. Visualize a mechanism illustration where the nitrogen group leaves the aromatic ring, releasing nitrogen gas and stabilizing the new product. Think of it as a polite exit, with the nitrogen gas waving goodbye, leaving behind a modified aromatic compound ready for the next step. Hello again, science sleuths. Ever wonder how chemists swap out a mysterious party guest called the Diazonium group for halogens or cyanides? Enter the Sandmeyer and Gattermann reactions, the dynamic duo of aromatic substitution. The Sandmeyer reaction is like the ultimate exchange game, where the diazonium group is replaced by chlorine, bromine, or cyanide ions by using copper, I, salts. Picture copper, I, chloride, copper, I, bromide, or copper, I, cyanide. These helpers are crucial players. The general reaction goes aromatic diazonium salt plus copper, I, salt yields the aryl halide or nitrile plus nitrogen gas escaping. Simply put, Arn to positive X negative plus Cux gives Arx plus nitrogen gas. On the other hand, the Gattermann reaction is the shortcut hero. Instead of isolating copper, I, salts, it uses copper powder with hydrogen halides like hydrochloric or hydrobromic acid to introduce halogens onto the aromatic ring directly and efficiently. No fancy copper salts, just good old copper metal and acid. Both reactions are essential because they allow us to add halogens or cyanides to aromatic rings, which expands the possibilities for creating new compounds used in medicines, materials, and organic synthesis. Imagine a reaction table comparing Sandmeyer conditions where you need specific copper, I, salts, and Gattermann conditions where you use copper powder with acids, but both ultimately swapping out the diazonium group for halogen or cyanide. Welcome back, inquisitive minds. Let's see how diazonium salts can transform into some useful functional groups like phenols or simple aromatic hydrocarbons. First, when benzene diazonium salts are warmed up with water, they get hydrolyzed, which means the diazonium group is replaced by a hydroxyl group, forming phenol. The chemical equation reads, benzene diazonium chloride plus water converts to phenol plus nitrogen gas plus hydrochloric acid. So, a water molecule grabs the place of the diazonium, releasing nitrogen gas into the air. Next, reduction with hypophosphorus acid or H3PO2 leads to replacing the diazonium group with hydrogen. This process is called deamination. Here's the reaction. Aromatic diazonium salt plus hypophosphorus acid gives the corresponding aromatic hydrocarbon plus nitrogen gas plus phosphorus acid, H3PO3. This step effectively removes the amino group from the aromatic ring. Why do we care? Because these transformations are vital steps in synthesizing phenols or preparing simpler aromatic compounds by removing amino groups. It's like swapping special outfits for casual wear, adapting molecules for different purposes. Picture a diagram showing two pathways starting from the diazonium salt, one leading to phenol by reaction with water, and the other to a hydrocarbon through reduction with hypophosphorus acid, both producing nitrogen gas as a signature exit. Hello, bright minds! Ready to add some color to our chemistry journey? Diazonium salts aren't just reactive, they are artists, painting vibrant dyes through coupling reactions. In these reactions, diazonium salts behave like electrophiles and couple with electron-rich aromatic compounds such as phenols and anilines to form azo compounds. Azo compounds have this distinctive nitrogen to nitrogen double bond, N equals N, linking to aromatic rings. These compounds are often brightly colored, and that's why they play starring roles in textile and food dye industries worldwide. Here's an example. Benzene diazonium chloride plus phenol in alkaline medium produces an azo dye called azophenol. In simple words, the diazonium ion couples with phenol to form a compound where two benzene rings are connected through this nitrogen double bond, creating vivid colors. Usually, this coupling happens at the para position on the ring unless that site is blocked, in which case ortho-coupling takes over, a bit like choosing the perfect seat in the theater to maximize the view. Picture a diagram illustrating how the azo dye forms. showing the resonance structures that stabilize this colorful molecule, explaining why these dyes have such lasting brilliance. Hey there, chemistry champs! Let's tackle a classic problem, converting aniline, which is C6H5NH2, into benzonitrile, C6H5CN. Ready? Let's begin. First, we do diazotization by treating aniline with nitrous acid and hydrochloric acid at cold temperatures. The reaction looks like this. Aniline plus nitrous acid plus hydrochloric acid yields benzene diazonium chloride plus 2 water molecules. Next comes the Sandmeyer reaction step, where benzene diazonium chloride reacts with copper I cyanide CuCN to replace the diazonium group with a cyanide, giving benzonitrile and nitrogen gas as a byproduct. So, step 1, form the diazonium salt. Step 2, use CuCN to substitute the nitrogen group with cyanide. The final product is benzonitrile, a useful compound in organic synthesis, and the nitrogen gas released confirms that the reaction went to completion, our invisible witness. Picture a stepwise diagram showing aniline converting first to benzene diazonium chloride, then proceeding to benzonitrile as nitrogen gas bubbles off, like a chemical relay race passing the baton smoothly. Alright, brilliant learners, time to wrap up a diazonium adventure. Recall that starting from aniline, reacting with nitrous acid and hydrochloric acid, we get benzene diazonium chloride plus water. This diazonium salt is a versatile intermediate. Using copper salts, for example, copper I chloride, bromide, or cyanide, we can replace the diazonium group with halogens or cyanides in reactions known as Sandmeyer reactions, releasing nitrogen gas. Alternatively, heating with water converts the diazonium salt into phenol and nitrogen gas, while reduction with hypophosphorus acid swaps the diazonium group for hydrogen, eliminating amino groups. Finally, coupling these diazonium salts with phenols or aromatic amines forms azo compounds, bright azo dyes used in industries. So, from one reactive intermediate, we can build a chemical toolkit for synthesizing a wide range of functional aromatic compounds, a true chemist's Swiss Army knife. That's it for today's lesson. Chemistry is endlessly fascinating when you can laugh and learn at the same time. See you in the next session.